and Happy New Year to everyone. And very pleased on behalf of the Mathematical Public Health Network and on behalf of my co-PI, Kumar, who is here, to welcome you to the first talk of the M4PH activities seminar series given by Professor Kolokolnikov from Dalhousie, and Professor Kolokolnikov is a Killing professor from Dalhousie, and is expert in PDE in multi-particle systems, dynamic systems, and pattern formations. That's the work that I've been closely following on. And I just mentioned to Theodore that his first paper on COVID-19 to understand the nonlinear incidence term in classical epidemiological model is the one that really interested. I heard his talk, PHUG groups, and I'm very pleased that he's with us today and gave this first lecture of the new year 2020. So Theodore, right now it's your time.
Okay, thank you so much for the invitation. It's a pleasure to be here. And let me try to share my screen. Okay, just a minute. Okay, everybody can see the screen? All right.
Yes, we can see it very well.
Okay, great. So today, the goal of my talk today is to try to say a few words about how one can model not just temporal evolution of epidemic, but spatio-temporal evolution, okay? And of course, there are many, many different models of this. So the approach that we are going to take, and this is joint work with my student Arvin Vaziry and Panos Kevrekidis from University of Massachusetts. The approach we're going to take is the one where we're going to extend an ODE model, such as an SIR model, but you can substitute your favorite model for instead of SIR, and we're going to extend it spatially to obtain a sort of a novel PDE model. Okay, so here is the very basic SIR. That is probably the simplest possible model of epidemic spread. And by the way, even though this is motivated by coronavirus, I'm not going to have very much data. I'll say a little bit about data at the end of my presentation, but this is mostly sort of a general talk. And then keep this in mind that I'm using this SIR model, but of course you can substitute any kind of complex model you want. The main idea that I want to talk about today is how to derive like a sort of a diffusion of the disease of the epidemic in space. Like, how does that look like? Okay, that is the key thing. But let me start with just the SIR model that we all know. And it has this kind of dynamics where you have some infection curve right here that kind of grows at the beginning exponentially, then finally it peaks, and then it decays, and the susceptible go into the infected class, and the infected class go into the recovered class. Okay, and so it's well known for the stability of this model. You just linearize this near the sort of the zero infection. So the question is, if you just introduce a little bit of infection, does it cause an outbreak? Okay, and so for that, if you just look at this equation, and then I can replace this at the onset of the outbreak, I would replace the S by like the initial S0, the initial population, and treat it as a constant. Okay, and then the infection just follow this ODE, which is simple exponential growth or decay. And so depending on this bracket here, it will either decay or grow. And that is So the term in this bracket controls whether the infection is stable or unstable. Stable means I will decay, no outbreak. Unstable means it's going to cause outbreak. Okay, and this is precisely what's called the R0. The reproduction number is just this ratio of beta S0 over gamma, and if it's bigger than 1, then you have an outbreak. Okay, so one of the goals for today's talk is to try to sort of generalize how does, so this R0 here doesn't have any spatial component. It's just like a single sort of well-mixed population. Okay, what if you have some variability? And in fact, you do have variability. Very naturally, a population is not homogeneous. Population is very heterogeneous. You have big cities and you have rural areas, and outbreaks typically first occur in big cities, then they propagate outwards towards the rural areas. And outbreaks happen much faster in big cities where the population density is higher. Okay, so this is one of the questions: how do we incorporate sort of the population density into the modeling? Okay, so there's a bunch of there's a lot of papers in the literature that looks something like this, and I just say, okay, it's not exactly, but there's a bunch of papers that roughly look like this. So they take sort of a standard SIR model or more complex model, usually it's a more complex one, and then they just add sort of the diffusion terms in each one of the components. In a susceptible, infected, and recovered component have some, they assume that they have some kind of diffusion. Okay, and this is modeled by this diffusion coefficient D. Right, and this SXX is, you know, the second derivative in space. And I say, this is the model, this is a PDE model, okay? So this is kind of a naive model, phenomenological model, trying to incorporate spatial component. There's a lot of papers in the literature that look like this, or some variation of this. And by variation, I mean, oftentimes they'll take this diffusion coefficients to be like space dependent, right? Maybe this depends on space, or all sorts of things like that. Okay. Now, what I claim is that this is actually sort of not. We don't think that this is quite right. Okay, and the problem is with this kind of modeling is, okay, forget about the disease, forget about the infection. Just think about like people moving around. Okay, what does the diffusion equation mean? Diffusion is, it means everything. If you start with some heterogeneous stuff, right? Then after diffusing, and everything becomes homogeneous, right? Just like, so you put some pollutant into a lake, and after a while it diffuses everywhere, and everywhere homogeneous in the lake becomes everywhere the same. Okay, so that's inherently what diffusion does. So if you don't have, like, so forget about all of this infection or whatever, just think of just people diffusing. What would that mean is that eventually the population will have a homogeneous density, right? So if you start with initial conditions that have like some heterogeneous population that look maybe like this, you know, you have some city here and some rural area, then after a while, if all you have is diffusion, you end up with like homogeneous population, right? That doesn't happen in reality. That's not at all realistic. Okay, and the reason why this doesn't happen is because, well, diffusion corresponds to just random walk, okay, Brownian motion, but that's not how people behave. People don't just randomly walk everywhere. What people do is they walk somewhere, but then they come back to where they came from, right? So you might go to grocery shopping, okay, or you might go to work, but then you come back home at the end of the day, right? You don't end up in some other place. Okay, so people don't diffuse, right? It's kind of the disease that diffuses in some sense. Now, of course, in this SIR type of models, we don't actually have a component for the disease itself. We don't track the individual viruses. We have the infected component, which consists of people. Okay, so how do we? So let's go back to the first principle and try to model this to try to understand how this works. Okay, so we're going to model the movement as follows. Okay, So we're going to discretize our space into bins like this, like S1, S2, etc. Okay, this bins here. And then Sj, right? So J will be the index corresponding to each bin. And then, so we have a bunch of different bins, and then we have different population inside each of the bin. Okay. And so what we're going to do is we're going to look at how many new infections per day in each bin will there be. And that I will denote by delta ij. Okay, so that's the number of new infections per day, right? In the bin J, Okay, and to simplify this modeling, and so I'm actually going to write this out a little bit. Yeah, this is what it looks like here, right? But to simplify this, I'll only assume that, for now anyway, only infected move around. So I'm sorry, this should be susceptible. Let's assume that only susceptible move around, and an infected and recovered remain still for now. And then later on, we'll generalize this later. Okay. So let me bring up a new sheet, and let's see how this looks like. So what I want to do is I want to compute delta ij. So that's the number of new infections per day. I'm sorry, I'm going to put this laptop on. Okay. So we have a grid. Okay, with so here's some bin J, and here's J plus 1, and here's J minus 1. Okay, and so how the infections happens is, well, you have some infection rate beta. Okay, and the infection can happen if you start in your own bin J and you interact with the infected individual in bin J. So that would be Ij times the number of susceptible in bin J. Okay. So the number of susceptible in bin J, I'm going to write it as follows. And let me explain why. So alpha here is going to be the rate with which individuals move to adjacent bin. Okay. Or the fraction of individuals fraction of infected, fraction of susceptible moving, let's say, to the right. And let's assume that the same alpha is also the fraction of the susceptible moving to the left. Okay, so the same number move to the left or to the right. So then the total number of the susceptibles interacting with the infectant in bin J within a day is S minus 2 alpha S. Okay. Now, then I have a term like this, beta times, so there's a bunch of them that move to the bin J plus 1, right? So they would be interacting with the bin at J plus 1. And that term looks like this. Okay. So this term represents those that susceptible individual, and there is alpha times Sj of them that went to work or went shopping. They went.
We cannot hear you anymore, Theodore.
Infection in the bin J, not in the bin J plus 1. Okay. And we similarly have another term, individuals going to the left. That looks like this. Okay. And so that's it. Right? That is the modeling of the infection. So let's see what are the consequences of this now. So this is this is written right here. Okay. So again, three terms. There is the daily infections of Sj in bin J, and the daily infections of Sj in bin J minus. And so then the model is the number of infected. The following day is the next infected current plus Ij, right? Plus this up here. And the number of susceptible, the following, well, it's the number of susceptible now minus the number of susceptible that got infected. And let me correct this error here. So this should be ij. Okay. So we add and subtract the same thing. Okay. And so that's the model. Okay. And by the way, please feel free to shout out questions. I can't see sort of any talk window, but if you have any questions, please just shout out and I'll answer them. It's nice to have these things interactive sometimes. All right, so okay, so that's the model. And now the next step is well, we want to take the continuum limit of this model. So what happens if I discretize, like I have a lot of different bins? Okay. And this is just a standard sort of approach where you basically you do Taylor series expansion. So if you rewrite this delta I, you end up with something that looks basically like, you know, the discretized second derivative operator. Okay. And so at leading order, you get this kind of ix term. Okay. So now let's plug that into the equation. And so at the end of the day, we get this. This is the PDE that we get. Okay. So here's some things to notice. First of all, so for the diffusion for the infected, you have a term that looks like this, right? So this is the diffusion of the infected. Note the important thing is that this is state-dependent diffusion. The number of susceptible S is inside the diffusion coefficient here, right? Okay. And it's taken with the plus sign here. And for this, hello?
Yes, Jianhong, I'm sorry to interrupt you. I just wondering why S appear inside the Laplacian.
Okay, yeah, so it comes from the modeling, right? So it's right here. So there's this S here. And that comes from the original, there's an S in here. So if you just rewrite this equation here for delta ij, that's just rewriting it over here, okay? And then the Sj will factor out throughout of those things, right? And so what you're left with is this diffusion term here, okay? And so it naturally appears in front of the, and then this is the Laplacian. So that naturally appears in front of the Laplacian. Does that answer your question?
Oh, yeah, I'm sorry, I misunderstood. I thought this delta is the Laplacian. No, yeah, you're right. So I'm sorry, yeah.
Okay, all right, thanks. And then, okay, so, and then the other interesting thing is that for the susceptibles, right, the diffusion for the susceptible, okay, there's a minus sign here, but it's not just diffusion, there's an IXX here in the susceptible terms as well, right? So it looks nothing like sort of the phenomenological model of just throwing a bunch of diffusion terms in the equations, okay? So this is sort of the model that's kind of motivated physically, if you like, right? Going from first principles modeling, okay, is you get this kind of diffusion. Okay. Now, I'll make a comment at this stage. In the derivation here, I've assumed that only the susceptibles move, okay? But that's just to simplify things, just for presentation purposes. And in fact, in the paper that in a paper, the preprint, we assume that all S, I, everybody moves in a, like, let's say S and I move in the same way or a different way or whatever. Basically, you end up with exactly the same kind of model. Okay, so even if you assume that both susceptible and infected move, you still end up with the same model. It just redefines this D. It just different constant for the D, but the model ends up being the same. Okay, all right. So let's have a look. So now let's see. Now that we have this model, let's play around with it and see what happens. So here's an example. Let's take this initial condition here. Okay, that looks something like this. That's heterogeneous. That's highly non-homogeneous. And so what I have to pay attention to, going back to the reproduction number, is I have gamma, the recovery rate. Okay, right here. The gamma, the recovery rate, is here. And so here I said beta equal to 1. And so the R0 sort of locally, it looks like S0 times beta over gamma. Oops, over gamma. So that's sort of without any, like that's just for the ODE. So if you think about this, when beta is equal to 0, when this blue and the red curves, if they cross, that's kind of locally pushes the R0 down. So in this case, because the blue curve is above the red curve, so the infection will spread everywhere locally. I mean, at least if the diffusion D was equal to 0, then it would still spread everywhere. So there is no suppression of infection anywhere in this particular example. And so here are the simulation results, just simulating that PDE. So here we have space X on the horizontal axis and time T on the vertical axis, right? And I show you two, so it's kind of a little bit hard to see in this picture, but basically this is a contour plot or color plot of the solution, X versus T. Okay, and so if you look at the infection, I introduced the infection right at the left endpoint over here. And so as time goes on, initially this sort of, there's kind of, you can think of it as having two cities separated by a rural area, right? So first, the left city is kind of gets infected, and D here is taken to be pretty small, all right? The diffusion is taken to be pretty small. So you have an infection that spreads throughout the left city over here, and then it spreads pretty quickly, right? This is almost flat. It almost kind of instantaneously spreads, and then it slows down, right? So the time passes here, it slows down. So for a while, not much happening, but it's spreading. The infection wave spreads through, and it goes through this rural area because rural area is still infectious, right? So just a little bit slower until it gets to the second city here, and then it very rapidly spreads throughout the entire second city, and then you get infection everywhere. Okay, and this is the top curve here is the top graph is the visualization of the number of susceptibles. Okay, the same thing. After this infection wave
condition. Sorry, Theodore, you
yeah, the boundary here I took to be Neumann boundary conditions. Okay, so like it's kind of a boundary here. It's not periodic. If it was periodic, it would look a little bit different. Yeah, thank you. This here is Neumann boundary condition. Okay, or a no flux boundary condition. Okay, so and now let's have a look at another example. So here's another example where, and this example is interesting because now I took so here it's the same as before, but I increased the recovery rate gamma so that I now have 3 regions. Like, so in this region here, the infection is suppressed. Okay, you're not going to have any because the effective R0 locally is negative, whereas in this region here, the other region, that's where you expect to see the infection. Okay, so you don't expect to see the infection in the green region, but you do expect to see it in the orange region. And so here's a simulation. This is what the simulation looks like. Let's start with the infected individuals on the right on this picture here. Okay, so I introduced a little bit of infection just at the left endpoint, and very quickly you see this peak of infection. Okay, but then what happens is it kind of rips through this left orange region, right? And then it comes and it kind of looks like, and then at about time t equal to 20, right? About here, it's already infected everybody in this left city, and then the infection dies out, right? And so up until t equal to 100, in this time, this is time here on this axis, in this region, you see that basically visually you don't see anything that happened. You don't observe any infection at all. Okay, it's as if the infection is gone. However, a little bit after this some time period of about 100, so it's quite a long time, eventually it still manages to sort of tunnel through this green region here and reappears at the right region. Okay, and it reappears at the maximum here where the R0 is, where the growth rate is kind of the fastest. And from there, it spreads out through the entire second orange region, right? And then eventually, once it spreads through that region, it then dies out, and that's the end of the end of the epidemic. Okay, and so similarly here, here's the plot of the susceptible population. As you can see here, you start with the initial conditions being in blue, then very quickly the susceptibles disappear from this region. In this green region, there's almost no infection. There's very little infection, so nothing much happens there until eventually it reappears here and then it affects the second cell. Okay, so this is what we call tunneling. So the infection manages to sort of tunnel through, even if you have some buffer zone in between the two cities. The model predicts that it's kind of very difficult to suppress, right, the infection, and eventually you do end up with the infection on the other side. Okay, so let me mention a few words about sort of stability and how can we sort of generalize this concept R0 for when you have spatial variability. Okay, so just like for the SIR model, if we just assume that I is very small, then up to leading order, and then we approximate S by S0, then the equation for I is approximated by this linear equation now, where we just assume that S is just constant at the onset of the outbreak, right? So initially, let's say the number of infected, even though it grows very fast, if the susceptible population is like whatever, 40 million in Canada, and the number of infected initially is maybe 100 or 1,000 or 10,000, is still very small. So it's still S0 here instead of S, right? And the same thing here. And so then the question of growth is we just linearize or separate variables for this PDE, right? We plug in this ansatz here, e to the lambda t times some phi of x, right? And when we get an eigenvalue problem for this lambda, which is the growth rate, okay? So we get this eigenvalue problem here, and this eigenvalue problem determines the stability, okay? So in other words, and it's subject to whatever the boundary conditions we have. Let's just take, for instance, we take here Neumann boundary conditions. You can take periodic boundary conditions, whatever you want, but this is a well-defined problem, and the solution to this problem is the lambda, okay? So lambda is the solution to this problem. Now, in general, like, so if S0 is like a constant, then lambda is very easy to solve, and then, it's well known. But if S0 is non-constant, then this is not sort of, there's no explicit solution for this, because it really depends on S0 of x. It's a second order linear ODE that we're dealing with. And so there's no like general solution for that for general S0. Nonetheless, there's a lot of questions. There's a lot. So there are some specific. There's some relevant limits that we can say a lot about. And one of the relevant limits, there's a couple of relevant limits, and one of them is D is very small. D represents like the speed with which, how many people per day leave the house, right? So if you have some health restriction or some travel restriction, then D may be decreased, for example, right? Or if you have a total lockdown, then D is like 0, basically. Okay, so that's what D represents. And so one of the relevant limits is what happens for small d, right? Maybe only some very few people leave the house, or maybe you have like total lockdown, right? So small d is a relevant limit. And another limit that a lot of things can be said about is the large d limit. Okay. But let me start first of all, and finally the other special is constant S0. Well, in that case, if the S0 is constant, and essentially you have lambda is going to be is basically this. So if S0 is constant, then essentially then phi will be just a constant as well, and lambda is this quantity here, okay, and it's unstable if lambda is positive, so that corresponds to the outbreak, and that basically recovers the R0. So for constant homogeneous population density, you get the same R0 as for the OD. And now let's look at the d equal to 0 limit, or very small. Okay, in that case, okay, I'm going to skip the stuff here, but basically for small d, we have a sort of an analog of R0. So R0 is going to be the same as before, except instead of just like constant S or average S, I'm going to put the maximum of S. Okay. And here S max prime to linear order is the same thing as the maximum of S. So that says that R0 is for small d, the outbreak is controlled by where the maximum population is, right? So where the maximum population is, that gives the stability. In fact, for d equal to exactly 0, right? The point where the outbreak is most likely to happen is the point where the population density is the maximum, right? That's what that says. And then there are some correction terms that can be computed. And so the interesting thing is that this is related to sort of the core problem. If you do the asymptotics, you end up with quantum harmonic oscillator to compute these corrections. So basically, you look at this, essentially you say, okay, you look at what happens near the maximum of the population density S, and you assume that it looks like a parabola, parabolic terms there, and then you get some basically quantum harmonic oscillator type of equation, and that's one limit. The other limit is large d, and then basically you get, for large d, if you compare this two equations, you get a similar kind of equation for R0, but you replace S rather than the maximum S, you have this harmonic average of S, okay, which is defined right here. Okay, it's 1 over the integral of 1 over the average of 1 over the population density, 1 over S. Okay, so so as an example, let's just look at an example. So here S0, I take it to be this quantity here, right? And then the maximum value is 1.5. So that's in a limit where d going to 0, right? And then the harmonic average of this, where this is in the limit as d is infinity or very large, then it can be computed explicitly for this example, and it's 0.866, whereas the average is 1, okay? So the harmonic average is actually less than the normal average, the mean, and that is always less than the maximum, okay? So in conclusion, all right, what it says that basically in the limit where d is very large, heterogeneity sort of helps to suppress the outbreak. It decreases the R's overall R0 value. But in the limit where d is very small, okay, the heterogeneity helps to initiate the outbreak, right? So so all else being equal, yeah. Okay, so finally, a few words about the speed of infection. So here we have, if you look at just basically, we use sort of KPP type of calculation, essentially, assuming that all coefficients evolve very slowly. In the limit where d is small, one can approximate the speed of the infection. So there's this infection wave that propagates throughout the domain, and you can see it in this picture here. In this picture here, right? So this is kind of the shape of this wave, and we can approximate the speed. At each point, there's different speed, okay? And using KPP type of calculation that I'm not going to go into, one obtains you can sort of write down the ODE for this propagation speed, okay, of the wave, of the front of the infection wave. You have some infection wave and it propagates, right, with some speed that's given here. Right. And it agrees pretty well with the numerics as shown in this picture. Okay, finally, I want to say a few words about sort of a case study is Nova Scotia, where we live, where I live, and my graduate student lives. So so this was done back in the summer. This work was done in the summer. So I have the data from summer, this past summer. But let me just, up to past summer, let me sort of say a few words about Nova Scotia. We've done very well overall in Canada with respect to suppressing COVID-19. It's been one of the best places to live if you if you worry about infection, up until the Omicron hit. And now actually our infection rate right now, I think, is one of the highest in the country. But up until that time, we've been doing very well. Anyway, so here's Nova Scotia, total population about 1 million people, right? And Halifax, or HRM, Halifax Regional Municipality here, the center of the province, has about 500,000 people, half the province. So there's a few other population centers. The second biggest population center is Sydney here in Cape Breton Island, okay? And here's the epidemic curve of the progression of the epidemic up until mid-July, when I generated this picture. So initially we had like a wave, and this is daily cases, daily COVID infection numbers, right? And so we had, like, in May 2020, when it first started, we had very strict health restrictions. There was, basically the first thing they did is they forbade all the travel, so nobody could come into the province without special permission. And if they did, they had to isolate for 2 weeks. And it was also like state home orders and so on. So we were able to suppress the initial peak. And then for a very long time, we basically had almost 0 cases. And whatever little cases that happened, like, were reported, all this is really like almost 0 cases. They were very quickly, we didn't really have an outbreak. There was one outbreak that happened in like November, a year ago. Well, it's all relative. So where we had a bit of outbreak, but they closed down the schools for a couple of weeks, and they closed all the restaurants down, and that suppressed the outbreak. And then again, up until the Delta, we had essentially 0 cases. So then the Delta came, and we had another big outbreak. Relatively speaking, it was still not so big numbers. It's only like 150 people per day infected at a maximum out of 1 million. Okay, that we also managed to suppress for school closures. The schools were closed for this period at the end of mid-April until the end of the schools, and then finally that's the progression. So what I want to concentrate on this is this peak here, and what happened in that peak. Okay, so what happened was there was let me see. Yeah. So what initially what happens at the start of the peak? It was the infection was imported from. There was a breach of quarantine, and people had a wedding around Halifax, anecdotally speaking, and that started the spread of the infection. Okay, and afterwards, almost all of the infections. So together, so almost all of the infections in this peak happened either in Halifax or in Sydney, the 2 biggest population centers. Everywhere else in the province, there was almost 0 cases, all right, very, very few. Okay, so almost all of these infections happened in those 2 peaks, and then like over 90%. Okay, and it's interesting that even though it started in Halifax, it kind of spread, it's kind of, I will use the word tonal, it tunneled through to Sydney. There was suspected, anecdotally what happened was there was a hockey game where Halifax team went to play in Sydney, and that's what started the infection wave in Sydney. That's anecdotally what happened. Nobody really knows for sure, but that's probably one of the things. And anyway, at any rate, the outbreak essentially was localized to both Sydney and Halifax. that's where all of the outbreak happened. And what's interesting is that even though Sydney is smaller than Halifax, like order 30,000 versus 500,000 people, the infection rate in Sydney was about 2.5 times bigger than it was in Halifax. But either way, both infections were quite small and eventually were suppressed after a couple of months of additional health measures and school closures, right? So this basically, I wanted to use this as an illustration of this tunneling effect and how difficult that can be to suppress the epidemic once it starts. Even though like the rest of the province, it looks like a kind of a buffer zone. So basically population density is sufficiently low in the rest of the province that it seems that like the effective R0 was below 0. But yet still the disease managed to sort of tunnel through to Sydney and cause an outbreak. Okay, I think that's all I wanted to say. And this is another illustration of the same picture that I was saying before. But yeah, I'll stop here and I'll take questions. Thank you.
Thank you. I forgot to ask Kumar to chair the question and QA, but I see you're chairing for the speaker. Kumar, any other questions? So while waiting for the comments, maybe I can ask a question based on especially your last examples you're showing in terms of Nova Scotia. So it really reflects the diffusion patterns in the modern area. Mainly, it's more of long-range dispersal rather than short-range diffusion. And the diffusion is not really from one grid to the next, but really is rather moving in way of more of anti-gravity, in the sense that you move from population density, high population density to next node high population density, because that's where the economic activities take place. Mm-hmm. So I'm wondering how this can be incorporated into your framework.
Oh yeah. So thank you for the question. That's actually something that we're looking into more at the moment. So first of all, let me just mention that the model that I presented only has like where the people travel to just the next neighbor, okay? And so it doesn't have this long-range diffusion. And even though it doesn't have the long-range diffusion, effectively you still see this tunneling behavior, right? Where that I've been talking about, where the disease can spread from one area, jump from one area to another, essentially. So even without the long-range diffusion, this model is sufficient to see that. But of course, you're right that it is important to model long-range diffusion, and the way to that we're working now at trying to incorporate this, and there's a couple of ways to do this. Basically, in this equation here, where we look at how the people move, instead of assuming that they just move to the left or to the right, we have some distribution of movement to all of the grid points, and maybe the weight of how many people move to which grid point.
Did we lose the signal?
I cannot hear. Looks like the voice dropped. Let's wait and.
Yeah, to generalize this to more sort of long-range diffusion, based, as you say, on sort of economic activity, or which can be represented, for example, by the population density itself.
Yes.
Martin has his hand up.
Yeah, Martin.
Yeah, I was just curious because you're looking for primarily focusing on whether or not a disease outbreak can happen at all, kind of thing. I was slightly curious to see if you've extended the approach with trying to understand if a disease can become endemic. in terms of a much more long-term sort of
Mhm.
approach with this model?
So, right, okay. So I think what one needs to do there is like here we start with the basic SIR model and extend it spatially, right? So for the endemic disease, you would have to add terms something like where the recovered lose the immunity, like something like minus mu r and then plus mu r, something like that here, right? To get some
Or demography.
endemic, yeah. But and that would actually, yeah. So if all you do is just that, right? Then that's a very simple extension of like you can basically, the model is the same as I have here. You know, you just add those extra terms in there, right? So yeah, so that certainly can be incorporated. We haven't tried to do that, but that's, so I did. Okay, so I'll say that a few words. So another question is, if you just put those terms in this extended model, then what happens is you do get endemic disease, but it doesn't have any variability. So it's basically comes to some constant state eventually, right? Just like for the ODE model, that constant. So it converges to some constant value, right? And it doesn't like it doesn't oscillate around it, or doesn't, or so it would be interesting to see how you can make it spatially oscillate. Is there some like ways to have, you know, like so spatially changing with time, and that I'm not sure how to do.
It's just because I'm curious, because there has been work with sort of more meta population, actual more some work with kind of demonstrating the I think was it measles cases in the UK, where they kind of demonstrated that it was due to meta population structures like this that was the reason why it was managing to stay around.
Oh, okay. Oh, that's interesting. Yeah.
I think it's in Matt Keeling's textbook. I was just curious if this approach could kind of come about the same thing.
Oh, okay. Okay. Oh, that's an interesting question. Yes, that's interesting. I haven't thought about that. Yeah. Thanks for pointing that out. I'll take a look. Maybe, right? I'm not sure.
Okay. Any other questions, comments?
Maybe I can ask the next question if.
Yeah.
I'm just first of all very interested in the topic, and also impressed with the way you presented. I really started to like the presentation using the iPad. It really allowed this you figures with two orange region,
Yep.
allowing growth in those regions. So
Mhm.
you would need very high density or very high transmission in the places where the infection is initiated, and then you would need really a fast diffusion so that the large infection in the first region, in the initiation area, can generate enough, or the not too many, because that reproduction number in the buffer zone is small, and allow those people to move very quickly towards the right hand side, right? So otherwise you won't be able to pass on those generate this transmission pass from left to right.
That's right.
So you might be able to calculate the critical diffusion rate.
Okay. So can we calculate the critical diffusion? So actually, so it's a little bit different for this continuum model, okay? Because yes, in so in the continuum model, it turns out that no matter how small diffusion rate you take, as long as you take it non-zero, right, it will eventually spread. The population will, the infection will jump from one city to the other. What happens is the time that it takes to jump increases as you decrease the diffusion. Okay.
Exactly.
All right. But it will eventually happen, at least in theory, right?
Yeah,
And
so
the
this
reason
is
is because it's a
yeah.
continuous model. So if you actually look at, so it's not, when you just plot the I here, all you see is basically you see nothing, right? You see like infection is completely gone, all right? But it turns out that if you plot like log of I, right? So what you see then is that the infection is still there, but it's exponentially small.
Yeah.
So that's why there's this effect of tunneling, because all you need is exponentially small amount to go through this buffer zone and end up here to cause the infection on another city, right? So yeah.
So that's actually the trouble with the continuous model. So
yeah,
once I goes to become positive, remain positive forever, and the small epsilon can accumulate a long time, and then
that's right.
Yeah.
So like it can be as small as like 10 to the minus 20 or something like that, right?
Right.
So for in reality, that would mean 0, because you know the number of people kind of quantize the thing, but in a continuum model that is actually non-zero and it causes the infection. Yeah, so there may be a ways to sort of to make this model more precise and introduce this quantization. I'm not sure. I haven't thought about that, right? But there may be some. It's an interesting question to think about.
That actually is a question that the my text team used to struggling on this for a long time. Is really how to build a transition from deterministic continuum model to probabilistic stochastic model. How to switch from deterministic to stochastic and switch on again. So this is exactly what this one shows, really exactly how important this issue is.
Actually, the other maybe I'll just make one quick comment, is that the simulations here are done at the PDE level, but underlying this is kind of like the discrete ODE system, which is right here, right? So so actually sort of in a sense, yeah, so there's a discrete system there that we can simulate and see if this, and sometimes when you simulate a discrete system, it can stop the wave, whereas the continuum system, the wave will propagate, but the discrete system sometimes stops the wave. I don't know. I haven't investigated this really in that detail. That's a good, it's an interesting question for sure.
Okay, are there any other questions or comments? I don't see any. Then let's thank our speaker again, Theodore.
Thank you.
Thank you very much for a very interesting talk, and probably we should all see the replay again to understand it even better. Good. Okay, thanks everyone. So do we know who the speaker next week is?
Sorry, I didn't keep along the list here, but I do know tomorrow there will be a very important talk for the next generation
Yes.
group. Yeah.
I can tell you who next week will be. So next week will be Amy Herford.
Okay.
Her titles to be announced, but I know it'll be interesting and valuable. So if you're available, please come along and enjoy.
Good. Okay. Thanks everyone, and see you next week, and see you also tomorrow then. Okay, bye. Bye.
Thank you.